Let us begin very gently and with patience by asking why linear algebra has such a central place in modern mathematics and in so many applications. Linear algebra is often described as the study of vectors and matrices, but that description is a little too narrow. A better description, for our purposes, is that linear algebra is the language of structure. It gives us a way to talk about patterns that repeat across many different settings, and it gives us a disciplined way to manipulate those patterns without getting lost. When we say structure, we mean something very practical. We mean that certain operations are allowed and certain rules are guaranteed. We know what it means to combine two objects, and we know what it means to scale an object, and we know that these actions behave consistently. When you have that kind of reliability, you can build theories that work not only for one type of object, but for many. And the word linear is also worth slowing down for. Linear relationships are, in a sense, the simplest non-trivial relationships you can study. They are not as trivial as everything is constant, but they are still simple enough to analyze and to predict. Linear models are the first place where we can combine simplicity with genuine expressive power. That is why linear algebra shows up everywhere in geometry, because lines and planes are linear, in differential equations, because linear approximations are the first and most stable approximations, in data analysis, because combining signals and scaling them is a basic act of measurement, in physics, because superposition is a linear idea, and in probability, because expectations and linear transformations are with especially clean behavior. It is worth repeating, calmly, linear algebra is not just a collection of techniques. It is a framework. It is a way to say, here is a world in which addition and scaling make sense, and here are the consequences. Once you learn this framework, you can reuse it in many settings without learning a brand new language each time. And if abstraction feels heavy at first, it helps to remember this: much of the abstraction here is not meant to make life harder. It is meant to make life clearer. It strips away unimportant details so that what remains can be applied again and again. Let us pause and reflect on that. The goal is clarity and reusability. The goal is to recognize one pattern wearing many costumes. With that big picture in mind, we can move slowly toward our first concrete idea, what we really mean by a vector. Many people first meet vectors as arrows drawn in the plane or in three-dimensional space. That picture is useful. An arrow can have a direction and a length, and you can add arrows by placing one after the other, and you can scale an arrow by stretching it or reversing its direction. But it is worth repeating, very gently, a vector is not essentially an arrow. An arrow is one example, one visualization, one helpful story. The deeper idea is that a vector is any object that you can add to other objects of the same kind, and that you can scale by numbers in a way that behaves consistently. So we keep coming back to two operations. First, addition. You take two vectors and you form a new vector. You stay in the same world. You do not leave the space of objects you are studying. Second, scaling. You take a vector and a number, and you form a new vector. Again, you stay in the same world. You are allowed to stretch, shrink, or reverse, depending on what scaling means in that context. If you keep those two actions in your mind, you can begin to see vectors everywhere. A vector can be a list of numbers. Not as a mere list for bookkeeping, but as an object you can add component by component, and scale by multiplying each component by the same number. A vector can be a signal, like a recorded sound. You can add two signals by adding the values at each time, and you can scale a signal by making it louder or quieter. A vector can be a function. You can add two functions by adding their outputs point by point, and you can scale a function by multiplying its output values by a number. A vector can be a sequence, an infinite list, as long as the same two actions make sense and behave well. So when we say vector, we are talking about a role an object can play. We are talking about behavior. The object must support addition and scaling, and it must do so in a coherent way. It is worth repeating in a slightly different way, the word vector is not tied to a picture. It is tied to operations. If the operations exist and obey the right rules, we call the objects vectors, no matter how abstract they seem. Let us pause and reflect. Addition and scaling. Combining and stretching. Mixing and amplifying. These are the basic actions, and once we have them, we can begin to define the setting in which they live. That setting is what we call a vector space. Now we come to a central idea, and we will take it slowly. What is a vector space? A vector space is a collection of objects, which we call vectors, together with two operations, addition and scaling, such that a certain list of rules is satisfied. You can think of these rules as the rules of the game. They tell you what you are allowed to do, and they guarantee that the results behave predictably. Let us describe these rules in words calmly, without symbols. First, when you add two vectors, you get a vector of the same kind. You do not leave the space. This is sometimes called closure under addition, but we can just say adding stays inside. Second, when you scale a vector by a number, you again get a vector of the same kind. Scaling stays inside. Third, addition is commutative. That means that the order of addition does not matter. If you add the first vector to the second, you get the same result as adding the second vector to the first. Fourth, addition is associative. That means that if you add three vectors, it does not matter how you group them. Add the first two, then add the third, or add the last two, then add the first. The final result is the same. Fifth, there is a special vector called the zero vector. When you add it to any vector, nothing changes. It acts like an additive identity. Sixth, every vector has an additive inverse. That means for any vector, there is another vector which, when added to it, produces the zero vector. In the arrow picture, this is the arrow pointing the opposite direction with the same length. In a function space, it is the function whose outputs are the negatives of the original. Then we have the scaling rules. Scaling by 1 does nothing. If you scale a vector by the number 1, you get the same vector. Scaling distributes over vector addition. If you add two vectors and then scale the result, that is the same as scaling each one first and then adding. Scaling distributes over number addition. If you take two numbers, add them, and scale a vector by their sum, that is the same as scaling the vector by each number separately and then adding those scale vectors. And finally, scaling is compatible with multiplying numbers. If you scale by one number and then scale by another, it is the same as scaling once by the product of those numbers. That is a long list, and it can feel like a lot, but it is worth pausing to say why these rules exist. They exist to guarantee consistency. They ensure that when you manipulate expressions built from addition and scaling, you do not run into contradictions. They ensure that you can simplify in the ways you expect. They ensure that there is a stable algebra of linear combinations, which we will talk about soon. It is worth repeating, the axioms are not arbitrary decorations. They are the minimal promises needed to make linear reasoning reliable. Now let us revisit a few examples, because examples help the rules feel natural. The space of lists of real numbers of a fixed length is a vector space. You add lists by adding corresponding entries. You scale by multiplying each entry. All the rules are satisfied. The space of polynomials is a vector space. You add polynomials by adding their coefficients. You scale by multiplying all coefficients by the same number. The zero polynomial plays the role of the zero vector, and each polynomial has a negative polynomial as its inverse. The space of functions from some domain to the real numbers is also a vector space, as long as we define addition point by point and scaling point by point. Again, the rules hold because ordinary real number addition and multiplication behave well. The space of sequences is another example, if addition and scaling are defined term by term. Let us pause and reflect. A vector space is a world where addition and scaling make sense and behave consistently. That is the core feeling. The formal list of rules simply protects that feeling. And once we have a vector space, we can begin to study smaller worlds inside it, worlds that inherit the same operations. Those are subspaces. A subspace is, very simply, a subset of a vector space that is itself a vector space, using the same addition and scaling as the larger space. That might sound circular, so we will say it more slowly. You start with a big vector space. It has its vectors and its operations. Then you take some smaller collection of vectors from within it. You keep the same operations, addition and scaling are performed exactly as they are in the big space. Now you ask, does this smaller collection behave like a complete vector space on its own? In other words, if I stay inside the smaller collection, can I add and scale and still remain inside it, and do all the vector space rules still hold? Because the big space already satisfies the rules, the only thing that can fail for the smaller collection is closure. The rules like commutativity and associativity are inherited automatically. The real question is whether the smaller collection stays closed under the operations. So there is a very practical test, and it is worth repeating several times because it is so central. To check whether a subset is a subspace, you mainly check three things in sequence. First, does it contain the zero vector? If the zero vector is missing, it cannot be a vector space, because a vector space must have an additive identity. Second, is it closed under addition? That means, if you take any two vectors from the subset and add them, is the result still in the subset? Third, is it closed under scaling? That means, if you take a vector from the subset and scale it by any number, is the result still in the subset? If those conditions hold, then the subset is a subspace. It is worth repeating in slightly different words. A subspace is a set of vectors that you can freely add and freely scale without ever leaving the set. Now let us connect this to geometry, because geometry offers a slow, comforting intuition. In the plane, consider a line that passes through the origin. If you take 2 points on that line, seen as vectors from the origin, and add them, you stay on the same line. If you scale a point on that line, you stay on the same line. So such a line is a subspace of the plane. In three-dimensional space, a plane that passes through the origin is a subspace. The key detail is through the origin. If a plane is shifted away from the origin, then it does not contain the zero vector, and it fails the subspace test immediately. That through the origin condition is not a technical nuisance. It reflects the requirement that the subspace must include the vector that acts like nothing, the neutral element for addition. Another important class of examples comes from systems of linear equations. If you consider the set of all solutions to a homogeneous system, meaning a system where the constant terms are zero, that set of solutions is a subspace. Why? Because if two vectors satisfy the homogeneous system, then their sum also satisfies it, and scaling a solution still satisfies it. And the zero vector is always a solution. But if the system is not homogeneous, meaning there is a non-zero constant term, then the set of solutions is usually not a subspace. It might be an affine set, like a shifted plane, but it will typically not contain the zero vector, and it will not be closed under scaling. And this brings us to an important warning that is worth repeating gently. Not every subset of a vector space is a subspace. Many subsets fail closure. Many fail the zero vector condition. Many are interesting sets, but they are not subspaces. So, whenever you are unsure, you return to the test contains the zero vector, closed under addition, closed under scaling. Let us pause and reflect. A subspace is a smaller world where the same linear operations still make sense, and you never escape the world by using those operations. Now that we understand subspaces as closed worlds, we can describe one of the most important subspaces generated from a set of vectors, the span. To span is to build everything you can from given pieces. Suppose you have a few vectors in a vector space. You might think of them as building blocks. The span of these vectors is the set of all vectors you can build by taking those building blocks, scaling them by numbers, and adding the results together. This is a key idea, and it is worth saying it again in slightly different language. To take the span of a set of vectors is to ask, what can I reach if I am allowed to mix these vectors in linear ways? And the phrase linear combination is simply the name for the mixing process. Choose numbers, scale each vector by its number, then add them up. So span is a reachability concept. It describes the region of the vector space you can access using those vectors if your only tools are scaling and addition. Let us pause and reflect on why this matters. In many applications, you have a collection of basic patterns and you want to express more complicated patterns as combinations of them. In signal processing, you might have basic waveforms and you want to build a signal as a mixture. In approximation theory, you might have simple functions and you want to build more complicated functions from them. In data analysis, you might have principal directions and you want to represent data points as mixtures of those directions. In all these cases, the span is a set of everything you can build. Now, it is also worth noticing something fundamental. The span of any set of vectors is automatically a subspace. Why? Because it is built by using addition and scaling. If you take two vectors that are each built from your building blocks and you add them, you still get something built from the same blocks. If you scale something built from your blocks, you still have something built from your blocks. And the zero vector is always included, because you can build it by scaling everything by zero. So span is not just any set. It is the smallest subspace that contains your given vectors. It is the minimal closed world that contains them. It is worth repeating that the span is the smallest subspace that contains the vectors. If you want a subspace that includes your vectors, you must at least include everything that can be formed by adding and scaling them, and that is exactly the span. Now let us consider the role of the coefficients, the numbers you use to scale. The coefficients control the mixing. They determine how much of each building block you use, and whether you reverse the direction, and how strongly you weight each piece. And the act of choosing coefficients and adding scaled vectors is the fundamental language sentence of linear algebra. Many later ideas are variations on the simple act. Let us pause and summarize quietly what we have. We have a vector space, a world where addition and scaling behave consistently. Inside it, we have subspaces, which are closed smaller worlds. Given some vectors, we can take their span, which is the set of all linear combinations of them, the smallest subspace containing them. Now we come to a subtle but extremely important question: when are the building blocks truly distinct, and when do some of them secretly repeat what the others can already do? That brings us to linear independence. Linear independence is one of those ideas that rewards slow repetition because it sits at the heart of what it means to have a good description of a space. Intuitively, a set of vectors is linearly independent if none of them is redundant. None of them can be built from the others by scaling and adding. Let us say that again. Independence means no vector in this set is secretly made from the others. If redundancy exists, then one of your building blocks is unnecessary because it contributes nothing new to what you can build. Now let us connect to geometry first, because the geometric intuition is soothing. In the plane, a single non-zero vector spans a line through the origin. If you add another vector that lies on that same line, then the second vector does not add a new direction. It is just a scaled version of the first. Those two vectors are dependent, because one can be made from the other. But if you take two vectors in the plane that do not lie on the same line through the origin, then together they can span the entire plane. In that case, near the vector is a linear combination of the other. They are independent. Each contributes a genuinely new direction. In three-dimensional space, you might have three vectors. If the third lies in the plane spanned by the first two, then it is redundant. It can be made from the other two, and the set is dependent. But if the third vector truly points out of that plane, adding a new dimension of reachability, then the three are independent. So geometrically, independence corresponds to adding new directions, not directions that were already available. Now let us connect that to the algebraic definition in words. A set of vectors is linearly independent if the only way to combine them with scaling and addition to get the zero vector is to choose all coefficients equal to zero. That sentence is worth repeating slowly, because it is the formal heart of the idea. If you take your vectors, scale them by numbers, and add them, you might sometimes get the zero vector. If there is a way to do that using not all zero coefficients, then you have found a dependency. You have shown that some mixture of them cancels out, which means at least one of them can be expressed using the others. But if the only way to reach the zero vector is the trivial way, where every coefficient is zero, then no cancellation combination exists and the set is independent. Let us pause and reflect on why the zero vector appears in this definition. The zero vector plays the role of nothing. If a non-trivial combination of your vectors produces nothing, that means the vectors can cancel each other, which reveals a hidden relationship among them. This hidden relationship is exactly what dependence means. Independence is the absence of such hidden relationships. Now, why does independence matter so much? One reason is uniqueness of representation. If your spanning set is independent, then every vector in the span can be represented in exactly one way as a linear combination of your building blocks. If your spanning set is dependent, then representations are not unique. You can describe the same vector in more than one way. Because there is redundancy, you can exploit to change coefficients without changing the result. And uniqueness is not just an aesthetic preference. It is a practical requirement in many contexts. If you want coordinates of a vector relative to certain building blocks, you want those coordinates to be well defined, not ambiguous. So independence gives you a stable coordinate system inside the span. It is worth repeating this connection. Independence removes redundancy, and removing redundancy gives uniqueness. Let us pause and summarize again, gently. Span tells you what you can build. Independence tells you whether your building blocks are truly necessary and whether the descriptions you build are unique. A set of vectors that spans a subspace and is independent is, in a deep sense, a perfect description of that subspace. Later we will call such a set a basis, but for now we are simply building the foundations. Before we end, let us return once more to the beginning and weave these ideas together. Let us conclude by gathering the threads we have been laying down, slowly and calmly. We began with the motivation. Linear algebra is the language of structure. It studies linear relationships, the simplest non-trivial relationships, and it does so in a way that can be reused across many areas of mathematics, science, and data. The abstraction is mainly there to give clarity and to make the ideas portable. Then we focused on vectors, not as arrows only, but as objects defined by behavior. A vector is something you can add to another of its kind, and something you can scale by a number, staying in the same world. Vectors can be arrows, but they can also be lists, signals, functions, sequences, polynomials. The picture changes, but the behavior stays. From there we defined a vector space as a world where addition and scaling follow consistent rules. Those rules guarantee that linear manipulation is reliable. You can regroup, reorder, distribute, and invert in predictable ways. The axioms are the rules of the game that make the game playable. Inside a vector space, we found subspaces, smaller worlds that remain closed under addition and scaling and contain the zero vector. We repeated the key test, zero vector included, closed under addition, closed under scaling. A plane through the origin is a subspace, a shifted plane is not. Solution sets of homogeneous systems are subspaces, non-homogeneous solution sets usually are not. Then we introduced span as everything you can build from given vectors using scaling and addition. Span is reachability. It is the smallest subspace containing your building blocks. And finally, we discussed linear independence as the absence of redundancy. No vector is secretly made from the others. Equivalently, the only way to combine the vectors to get the zero vector is to use all zero coefficients. Independence matters because it gives uniqueness of representation, a stable, unambiguous way to describe vectors in the span. It is worth repeating, one last time, the calm rhythm of the foundations. We have a world, the vector space. We have smaller closed worlds, the subspaces. We have a way to generate a subspace from building blocks, the span. And we have a criterion for whether the building blocks are genuinely distinct, linear independence. If you carry these ideas with you, even in a quiet, drifting way, you will find that much of linear algebra becomes a slow unfolding of these same themes, combining, scaling, building, and removing redundancy, all under a consistent set of rules. And with that, we can rest in the feeling that the foundations are in place, a steady framework, a reliable structure, and a language that will keep returning again and again in many different mathematical worlds.